This is the lecture for Friday, March 15th. We will be talking about electromagnetic decays. There are two types of electromagnetic decays we will talk about. One is gamma ray emission, where you see the photon that's being emitted with an energy typically on the order of mega electron volts. We can also see internal conversion, which we'll talk about in a moment. And that's abbreviated IC. That's when one of the interior electrons actually captures the photon, and so you don't actually see the photon as a result. Now, in both of these decays, the neutron number, the proton number, and the total nuclear number do not change. There's no change in particle numbers of any types. So you can think of this as simply a lowering of the excitation energy, as well as the fact that the photon will carry some angular momentum with it. Now, in gamma ray emission, most of this emitted energy appears in the form of a photon. You could have some of the energy absorbed by the recoil of the nucleus, but this tends to be quite small. Now, these emitted photons then have a very sharp energy signature. And so you can see this diagram here. Suppose this energy level 1 is the ground state of the nucleus. Energy level 2 is some excited state. Energy 3 is another excited state above that. And energy state 4 is another excited state above those. We can then have transitions where excited state number 4 spits out a gamma ray, and it drops down to state 3. It could actually spit out a gamma ray and drop down to state 2, or it could spit out a gamma ray photon and drop down to 1, or you could be in level 3 and jump down to 2, or jump down to 1, or you could be in 2 and you can jump down to 1. And so as a result, you see these very narrow spikes, I guess, of the energy distribution, and that gives you a sense of what the energy levels will look like just from these gamma ray photons. Okay, now just a few comments about gamma ray radiation. Of the various types of radiation, we can talk about alpha radiation, alpha ray or alpha particle radiation, beta radiation, which is electrons. But the gamma rays, which are photons, are the most penetrating, and it requires a lot of work to actually shield yourself to protect your tissue from being damaged by the gamma rays. And sort of as a historical side note, well, actually more cultural side note, there's this movie, you've probably heard of it, and there's Dr. Strangelove. If you're not sure who Dr. Strangelove is, just Google Dr. Strangelove and you'll see the reference. There's the discussion of a doomsday device where you actually take cobalt-60. So the way you make cobalt-60 is actually you radiate cobalt-59 with neutrons using some sort of a device, a bomb or something. And so you produce then cobalt-60, which is relatively long-lived. It has a half-life of about 5.3 years. But now, when the cobalt-60 beta decays, one of the neutrons converts into a proton, and we get nickel-60. What you find is that after the gamma ray occurs, after the beta decay occurs, the nickel-60 is in an excited state, which then can emit two gamma rays with energies of 1.17 and 1.23 MeV. And these gamma rays are quite bad for tissues. And so this was the idea of the doomsday machine that was in this movie. Now, there is a second type of electromagnetic decay that I mentioned, and that's internal conversion. So in internal conversion decay, or IC decay, this emitted energy is actually transferred to an orbital electron, typically one of the interior s shell electrons, 1s electrons that are close to the nucleus. And this electron then jumps up to some excited state, or it's actually knocked out, and carries away most of the decay energy. So typically these electromagnetic transitions take place in a rather short period of time, 10 to the minus 15, 10 to the minus 13. Now, occasionally you see electromagnetic transitions with a lifetime about a nanosecond or greater. Now, these require some sort of mechanism to block the decay, to make the decay a little bit more difficult. And so this can occur if there's a rather big difference in the angular momentum between two neighboring energy levels. So this is an example of one of these isomeric transitions where these neighboring states have rather big differences in angular momentum. So here you can see something quite interesting where we have zinc 69, and it decays with beta decays with a half-life of about 56 minutes. And what's interesting is that there's an excited state. So the ground state is a 1/2 minus. The excited state is in a 9/2 plus parity state. So spin 9/2 plus parity. The ground state is spin 1/2 minus parity. And the decay of the excited state is actually 13 hours, which is quite a bit longer than the lifetime of the half-life of the ground state. So as a result, the excited state actually lives longer, and that's because of the big spin difference between the 9/2 plus and the 1/2 minus. And this transition, this gamma ray transition, is quite suppressed because of that angular momentum difference. So let's talk about how this occurs. This is actually not a gamma ray transition, but it's actually an internal conversion. Internal transition. Okay, now, so let's talk about gamma ray decay. So we have a nucleus. It shoots off a photon. Now, for a photon, the momentum and the energy of the photon, they're just related by a factor of c. So if I take the momentum of the photon, multiply by c, because it's a massless particle, the energy will just be the momentum times c. But from momentum conservation, if the photon is moving with a momentum p gamma, then I have a recoil of the nucleus going in the opposite direction with the same magnitude. Okay. So if I want to then calculate the kinetic energy of the recoil of the nucleus, it will be p squared e recoil squared over 2 times the mass of the nucleus, the recoil mass. And so that's the same as p gamma squared, which is then, I can relate this as p gamma is e gamma over c, so that's why I can write this as e gamma squared over c squared. Now, typically the energies of the photons we're interested is going to be maybe 1 to mega electron volts, whereas the rest energy mc squared for the nucleus will typically be several or tens or even hundreds of thousands, 100 times 1,000 MeV. So the mass of a nucleon is like 939 MeV multiplied by 2, but then you have to multiply by A, the number of nucleons. So you can see the denominator is quite large compared to something in units of MeV that would be about 1 MeV squared. So as a result, the recoil energy is going to be much less than a mega electron volt. So it'll be a very small energy relative to the energy of the photon. So that's by the way why these energy signatures that we saw before are so sharp. The recoil energies are really quite small. Okay, So now we're going to talk about the classification of these electromagnetic decays. So the initial and final states of the nucleus we'll measure them, and they will have some definite angular momentum and parity. But the photon will carry away some amount of that angular momentum. So you can think about the initial nucleus as having angular momentum I initial. Okay, so we'll just write as I initial. But then it's going to decay, and so the photon is going to carry away some angular momentum L, which I'll write L for the photon. But then there'll be some leftover angular momentum from of the nucleus. So we can think about it doing angular momentum addition. That I have angular momentum I, and then I have angular momentum L plus IF, and so I have to think about doing angular momentum addition between these three values. And so we learned how to do angular momentum addition. And so the value, what are the possible values for L? It can go between the difference between these two angular momenta, I minus IF, absolute value, so that you don't have to worry about which one is larger than the other, up to the sum of the two, okay, II plus IF. All right, so that gives us the that will give us the range for the angular momentum of the photon. So if you want to put in the factors of h bar, the angular momentum carried away by the photon is L times h bar. So now let's dig a little bit deeper. What we're going to do is we're going to talk about a multipole expansion. So this is hopefully something, well, we have talked about this before, where we have monopole L equals to 0, we have L equals to 1, the dipole, L equals to 2, the quadrupole, L equals 3, the octupole, and if you go to L equals 4, the hexadecapole. So we're going to do an expansion in multipoles. Okay. So we can talk about these electromagnetic decays in terms of these multipole expansions, but we can also talk about whether it's an electric transition or a magnetic transition. So what is electric versus magnetic? As you might expect, it has something to do with electric fields and magnetic fields. So you can think about the radiation from for the electric case is due to a shift in the charge distribution. Okay, something's going on with the charge distribution, whereas the magnetic radiation is caused by some shift in the current distribution. So the current distribution, that is related to the circulation of charge, how it goes around, some angular momentum of a particle that's charged, or you can think about the spin of, for example, the proton or the neutron. So based upon these two possibilities, we have these two types of transitions. Okay? And there will be a change in the parity depending on the angular momentum as well as whether it's an electric or magnetic transition. Let me just go to the rules, and then I will actually I will give some derivations in a moment, but let me just give you some of the basics here. So the first thing I should mention is that L equals to 0, that's what we call the monopole. There is no electric monopole transition you can make with a real photon. This simply is a result of Gauss's law, or the fact that if we had a monopole transition, so in other words, the idea is we have some sort of spherically symmetrical distribution of electric fields changing in time. If we have, just think about it, you have a sphere, we have electric field pointing out of the sphere, and we want this to be changing with time. What we're doing is we're saying that the flux of the sphere would be, the electric flux of the sphere will be changing with time, but that actually requires that the charge inside of the sphere is changing with time, and that's not allowed by charge conservation. So we can't have a monopole radiation as a result, okay, for the electric case. Now, how about for the magnetic case? Well, that's even simpler. We do not have magnetic monopoles to begin with, and so that's sort of ruled out from the beginning. So we actually start off with L equals to 1. Okay, so this is L equals to 1. The change in the angular momentum, all right? So this is just the angular momentum, L equals to 1. And so E1, so the way you say it is E for electric, M for magnetic, and dipoles 1, quadrupoles 2, and so on. So the first one we have is the electric dipole, and that's L equals to 1. And this delta pi means whether there's a change in parity. In other words, that should say change in parity. In other words, there's a parity flip. All right? And if you just remember for the dipole, there's a very simple rule here for the electric transitions that minus 1 raised to the nth power gives you the parity of the distribution. And so if I have L equals to 1, there's a minus 1 for L equals to 1. And so there is a flip in the parity. It's flipped from positive to negative or negative to positive. And so if I go to E2, then that's L equals to 2, then minus 1 to L equals to 2, that's plus 1. So there's no change in parity. Okay, so L equals to 3, then there's a change in parity. Okay, and then L equals to 4, there is no change in parity. It's just minus 1 to the L. Now for the magnetic dipole, quadrupole, octupole, hexadecapole, it's the same sort of, it flips signs with L. However, it starts off at L equals to 1 with no change in parity. And that's because there's actually an extra cross product in the definition of the magnetic multipoles. I will show that to you in just a few minutes when we actually do some of the math behind this. There's going to be, it comes from the fact that we have a magnetic moment here, which is, will change the parity. Okay, let's go on. By the way, if you have questions about this lecture, please email me, and I'll be happy to answer. Okay, so let's do an example. Let's say we have electromagnetic transition going from sodium 23, going from an excited state that's 2.08 MeV above the ground state, a 7 halves plus state, going down to the 3 halves plus ground state. And so this is the initial value of angular momentum, I. By the way, I have to admit, I usually use J for this symbol, but this is the notation that people often do use in nuclear physics for this. And the angular momentum for the ground state is 3 halves. Okay, so what we do is we take the difference between the two, what is 7 halves, the bigger one minus the smaller one, okay, and that gives me 4 over 2, which is 2. So we go from 2 for the minimum, and the maximum you can get is the addition of the 2, so that's 5. So L can be between 2 and 5, all right, so that's the possible values for L. And then we can just simply go through the possible transitions. All right. So first note that we have the same parity, so we don't want to change the parity. Okay. So if we do L equals to 2, if we do an electric transition, and then the parity of the photon, if you like, is minus 1 to the L, so that will be plus 1. So that will not change the parity. There's no flip. There's no minus sign here. So in that case, an E2 transition is allowed. E2 transition, we get minus 1 to the raised to this L equals to 2. That's plus 1. So it does not change the parity. Just think about this plus 1 as multiplying the parity of the original state. And so it's not changing the sign. Now, if we do L equals to 3, in that case, then the electric transitions will flip the parity, so that's not good. But if we have the magnetic transition, there's an extra minus sign. So the rule for that is there's a minus times minus 1 raised to the L's power. And so in that case, with L equals to 3, then we get plus 1, which is okay. So there's no change in parity. M equals to 3, and you can figure out what the pattern is. E4 is allowed, and M5 is allowed. So these are the transitions that are allowed from these between these two states. Okay. Again, if you have questions about this, please email me, or you can ask me when we do the second part of this lecture on Monday, March 18th. Okay. Now, I already mentioned that there is no L equals to 0 transitions, no monopole transitions. And so as a result, it's not possible to do a transition from a 0 state, as angular momentum 0 state, to another angular momentum 0 state. Okay. Why is that? Because if you start at angular momentum 0 and you end at angular momentum 0, the photon has to have angular momentum 0, but I just mentioned there's no monopole transition. There's no monopole photon sort of distribution you can get. Now, it is, however, allowed by internal conversion. That's because the photon is actually what's called virtual. It's actually absorbed by the electron. The electron is the thing that's kicked out, and that can be that can actually you can have a transition that way. Okay, and now. So a general rule I should mention is that you can get both electric and magnetic matrix elements contributing to a given decay probability. Okay. So the other thing, general rules to mention is that the lowest multipolarity is most favored. So we'll go through that in a moment. So in other words, the smallest L possible gives the biggest transition likelihood. Okay. And another rule is that the magnetic matrix elements tend to be smaller than the electric matrix elements for the same L. So now this is just a rough estimate, but the E2 and the M1 transitions actually are very typically about the same size for a lot of nuclei. So here is the promised math behind what's going on here. So the electric charge density, so if I have point particles with charge EA, then if I just sum over the positions of these point particles, then I get the electric charge distribution. Okay, and then this electric multipole, I have to, I'll fix that on the notes. The electric multipole operator will then be the integral of the charge density against this, what's called a solid spherical harmonic. It's a spherical harmonic that's a function of this angle, or if you want unit vector, this is the vector r divided by the magnitude of r. But you multiply the spherical harmonic by r raised to the lth power, and this makes this guy actually a polynomial in the vector r. Okay, you're just then taking these moments of the charge distribution. For example, if I have the multipole operator, the monopole operator, L equals 0, M equals to 0. So then this electric monopole operator will just be, I have rho E times y0, 0, which is just 1 over square root of 4 pi. And so we end up getting, if we integrate the charge density, then we just get 1 over square root of 4 pi times the charge, which is a z times the electric charge of the nucleus. Okay. Now, we can also think about the magnetic charge density, which may sound a little bit confusing because you know there are no magnetic monopoles, but we can define, sort of in quotation marks, the magnetic charge density as minus the divergence of the magnetic moment density. Okay, so if you integrate over the magnetic charge density over all space, you can then use Gauss's law to convert this to a surface integral of the magnetic moment density. So what am I talking about? If I do d3r of rho m of r, then that will be minus, just plugging in here, d3r del m r here. Then I can convert this into a surface integral at infinity, okay, by the divergence theorem, or whatever, however you want to think of this. I should say divergence theorem. But the magnetic moment density vanishes at infinity, and so this will actually go to 0. So this guy is equal to 0. Right? Now, I can then use this magnetic charge density to define the magnetic multipole operator by doing the same thing I did for the charge density, but just replacing the magnetic charge density here. What I did for the electric charge density, I will do for the magnetic charge density. Just integrate with this solid spherical harmonic, r raised to the nth power times the spherical harmonic r vector divided by magnitude of r. And I can then plug in what I had for rho m, and then I can integrate by parts and then throw this this derivative onto the other term here, RL times YLM, and then this will be dotted with the magnetic moment density. Okay, and so this is actually how we can then calculate the magnetic multipole operator. And so what you can then do is you can just take the, so this is just the magnetic moment density. So for example, when we were talking about the shell model, we talked about how to get the magnetic moment for a single nucleon in a given shell model orbital. And so you can use those results here to get the expectation value of this operator. Right? Okay, so now talking about the shell model, we can talk about shell model estimates of the electromagnetic transition rates. So we can then think about, so we're making an approximation here, which does not actually always work. In fact, very often it doesn't work. We can then model the electromagnetic transitions in the shell model as being caused by the change in a single nucleon from one shell orbital to another. Okay, so we're just thinking about there's this one nucleon that switches from one orbital to another, and it spits out a photon as a result. And so this very simple estimate, where we're then taking the magnetic moment of that nucleon, of that one nucleon, you're taking into account its spin, the magnetic moment from its intrinsic spin, and the magnetic moment from its motion if it's a proton. If it's a neutron, then there's no additional term, it's just from the spin. Okay, so these estimates that you get from a single particle transition are what are called Weisskopf single particle estimates, named after Victor Weisskopf. All right, so you can then use your harmonic oscillator wave functions and use these single orbital estimates to actually calculate what these transitions are. It's just basically calculating, sandwich this operator here between the single particle orbitals, and you can then get these formulas. I'm not going to go through that, but you end up with a formula that looks something like this. The transition rate here. So there's some interesting things here. The key thing I want to point out is there's a dependence. So k is the momentum or the wave number of the photon. So there's a dependence k to the 2l plus 1. Okay, and so because the photon momentum is proportional to the energy, it's also proportional to the energy of the photon raised to the 2l plus 1 power. So as L gets larger, because E tends to be, we typically think about the photons as being rather soft in energy on the MeV scale. And so these things tend to get smaller as we raise them to higher powers. Okay, so there are various prefactors. By the way, if you have never seen this before, this is just basically the odd factorial expression. So if you have these are always odd numbers. So if you write something like 5 double factorial, that's 5 times 3 times 1, where you skip the even numbers and writing out the factorial. So then here are for these branching these rates, these B of E L's. This is how they're called, B of E L or B of EML. And this SP stands for single particle estimate. And so this is a number, we saw this before, it's like 1.27 femtometers. R0, A is the number of nucleons, so you can get this kind of an estimate. So it's, as you increase the number, as you have more nucleons, this gets larger. And so then we also have, so E squared, we also have it in terms of these Bohr magnetons. Okay, and so you can see what this looks like. Let me maybe, well, the resolution is not that great, but you can see, I'll try to explain what's going on here. This is the energy increasing this way in a log scale. This is a double, actually both axes are in log scales. And so this is the L equals 1 transitions, okay? And you can see it has smallest slope, so that's because of the dependence that it goes as e to the power 2L plus 1. Okay. And then we have the L equals to 2 transitions, okay? And if you're wondering why there's several different lines, these are for different values of A. A is equal to 20, 50, 130, and 220. And you can see there's some small differences between the two. But the slopes, the asymptotic slopes are all the same. And this has a steeper slope because it's raised to the power e is raised to the power 2L plus 1. And then this is for L equals to 3, L equals 4, L equals to 5. And this is for one is the electric and one is the magnetics. This looks like electric. Yeah, that's an E and that's an M there. Okay. So here are the same thing in numbers. So here are the Weisskopf single particle transition estimates for the multipole L equals 1. It's E gamma raised to the 3rd power. There's a prefactor here. Okay. And so for the M1, 3.15 to the 10^13 E gamma cubed here. Okay, and so you can just read off and use E gamma to the 5th power, E gamma to the 5th power. That's how it scales with the number of nucleons and the energy. And so the lower the value of L, typically the larger the transition rate is. Okay, I believe this will be where we'll stop. So these shell model estimates of the electromagnetic transition rates are usually good within a factor of about 10. Okay, so when they get the answer wrong, they're usually like a factor of 6, 7, 8, 9, 10 off. But this is a good way of actually calibrating what the actual transition rate is. You can say the actual transition rate for the gamma ray transition is something times the Weisskopf estimate. So that's sort of a standard candle. And so it's written as capital W period UW for Weisskopf units. So I'll stop there. If you have any questions, please email me or you can ask me on Monday. And don't forget then, after watching this video, to also email me your summary. Thanks very much for watching.